MAP4C 7.2, the present value of an annuity. The present value of an annuity is the principal that must be invested today to provide the regular payments of an annuity. So earlier we have discussed that an annuity is a series of regular payments. But the difference is, in this case, we are talking about a large amount that is deposited and we'll be making withdrawals from that amount at regular increments. So this is similar to what happens with retirement. We save up as much as we can with a retirement fund, but that's putting money into an account to get a total. With the present value, we were wondering at the moment when we retire, we stop working, and we need to live off of our savings. But it doesn't make sense to withdraw all of the money all at once because we could take some of that money and the amount that is still invested could be earning interest while we're making regular withdrawals. So this formula applies to that situation. We can figure out what value now, the present value, needs to be invested so that we can get regular payments, R, some amount of money, for a certain period of time. So N is the number of compounding periods, and the I and N variables must be adjusted in the same way that we did for compound interest. The formula for calculating the interest, the capital I, refers to the total interest. And we get the total interest by looking at R times N. So the variable R represents the payments that we are receiving, multiplied by N, the number of compounding periods, and that's the number of times that we receive it, minus the present value. So think of the present value as at the start of the investment. And R times N would be like the end of the investment. How much did you withdraw with these regular payments? The difference between those two will tell you how much interest was earned during the duration of this investment. This formula applies to a specific case. We call it a simple ordinary annuity. The present value formula can only be used when the payment interval is the same as the compounding period. The payment is made at the end of each compounding period, and the first payment is made at the end of the first compounding period. Let's look at an example. Providing for an annuity. Victor wants to withdraw $700 at the end of each month for 8 months, starting 1 month from now. His bank account earns 5.4% per year compounded monthly. The first thing I'd like to point out is that this is an annuity. We want to withdraw $700 at the end of each month, so it's regularly occurring. And what makes this different than in previous sections, we want to know how much must Victor deposit in his bank account today to pay for the withdrawals. So all of the money is already deposited, and we're now withdrawing from that amount. So make sure that you do not confuse this with section 7.1, where we're regularly starting from nothing, putting money into the account. This is different. This is all of the money's in the account and slowly pulling away. So section 7.1, the amount of an annuity, can be thought of like a registered retirement savings plan. And then this section, the present value of an annuity, could be thought of as drawing money from a pension. So let's look at our given information. Victor wants to withdraw $700 at the end of each month for 8 months. That's a regular payment, R. The interest rate is 5.4% per year. That's the annual percentage rate. But we have to adjust it for the moment of calculating. The period that we calculate it is monthly. So we'll take I, which is 0.054, this as a decimal, divided by 12. And that is equal to 0.0045. So at each compounding interval, this much interest is being calculated based on the amount that's invested. N is the number of compounding periods. So if we are making withdrawals at the end of each month for 8 months, there's a total of 8 compounding periods. What is unknown is the present value. How much needs to be into this account today to be able to slowly make withdrawals from it over the course of our retirement? Now in this case here we're talking about a loan, but the same principle applies. we are going to be withdrawing $700 each month for 8 months. So that being said, the present value, meaning how much today is equal to this amount, is $5,488.28. How much interest does Victor pay? So what we need to think of is we have all the information that we need in the previous example. But the formula, interest is equal to R times N, this is the regular payment, 700, times the number of times that we receive that payment, or compounding intervals. There's 8 because it's for 8 months. And then we're going to subtract the present value. That's what it was at the beginning. So the reason why we would want to be withdrawing money in this fashion is because the money, we're not going to use it all at once the moment that we retire. Otherwise, we'd be out of money and we'd have to continue to work. The advantage of having it invested and drawing from it slowly is that the amount that is still in the account is receiving or earning interest. So $5,600 is the total of what it pays out over this 8-month period. And that difference is $111.71. So that's the incentive for not withdrawing all the money at once. You can earn interest with the money that's invested. This spreadsheet is going to help us track what's happening. So we were told that this amount is equivalent to that payment method over time of $700 each month for 8 months. And let's see this in a spreadsheet. So I took the amount that we calculated is equivalent to this payment period of $700 a month for 8 months, and we'll see if this holds true. We have the amount copied here. The interest is based on this amount. So our interest was, at the time of calculating, 0.0045 multiplied by this amount, and you get your withdrawal at the end of the month. And our ending balance is $4,812.98. So what's happening is this money was left inside of the account for the entire month. It earned interest because it was deposited. And then we have to actually subtract the withdrawal because this number is representing the amount of money that is in the account of the investment. So this withdrawal goes towards us for spending, but it's not what is being represented by the starting and ending balance. That represents how much money is left altogether. So the starting balance of the next period is the same as the ending balance of the previous. And the interest, we'll use that same value, 0.0045 times the amount at the beginning, the starting balance. Notice that the total interest that's being earned at this point is less. And the reason why is because there's less money in the account overall. We withdrew $700, so our total went down. And therefore, there's less money accumulating interest over time. So we continue this process, and at the end, we're barely earning any interest at all because there's barely any balance left in the account. And at our final payment, we'll have $0 left. And that is how we plan to use our pension. So, our next example here. Calculating the amount needed at retirement. Azadeh plans to retire at age 60. She would like to have enough money saved in her retirement account so she can withdraw $7,500 every 3 months for 25 years, starting 3 months after she retires. So notice that every 3 months is quarterly. A, how much does Azadeh deposit at retirement at 9% per year compounded quarterly to provide for the annuity? Notice that the payment frequency and the compounding frequency is the same, both quarterly. The regular amount that we would like to withdraw is $7,500. The interest rate needs to be adjusted because it's quarterly. Every 3 months is quarterly. Divide 9%, the annual percentage rate, by 4 to get our calculation factor for interest. The number of compounding periods, if it's 4 times per year and this is for 25 years, then that would be 100 payments or 100 compounding intervals. So what's unknown is the present value, and we can substitute into our equation and solve and determine that this is $297,313.05. So that's how much money needs to be paid at the beginning of retirement to keep receiving these payments. Now 9% is a very high percentage rate, but let's take a look at the interest for this. How much interest will Azaday earn during retirement? And we'll use our formula. Calculate the sum of the payments. That's 7,500 times 100 intervals. That's $750,000. We'll subtract the present value, what it was worth at the beginning, and this is what it's worth at the end. The difference between the two is the interest that has incurred over the 25-year period. So these numbers, remember, this is all dependent on the interest rates, but this is a pretty sizable amount because it's over a very long period of time. We could investigate here just to support this answer. Notice that I took the same starting balance that we had. We take the interest based on, so that was our factor for interest, multiply it by the starting balance to calculate the interest in each interval. The payment will always be $7,500 because we determine this present value based on what payment we wanted to receive are. And the ending balance is made up of, you take your starting balance, you're going to add the interest because that's how much is in the account that you're drawing from. And the payment that is to us, we're taking that away from the total because we're talking about the total amount that is in the account, our pension at this point. And over time, we will see the difference between the interest and that will decrease in time. And there's 100 different periods or compounding intervals. So you look at this here, we approximately get 0 by the end of this, and the total of the interest corresponds to our calculation in the Word document. Just going to verify. One moment. So, as mentioned, the sum of the payments is $750,000, and the interest that's accumulated is here. Now, this is off by 4 cents when we're talking about very large numbers, and enough rounding over time does result in a little bit of fluctuation, but overall, the pension fund will be out. Essentially 0. One last example. Most loans are repaid by making equal monthly payments over a fixed period of time. These payments form an annuity whose present value is the principal borrowed. When all the payments are made, both the principal borrowed and the interest due will have been paid. Sema plans to buy a used car. She can afford monthly car loan payments of $300. The car dealer offers Sema a loan of 6.9% per year, compounded monthly for 3 years. The first payment will be made 1 month from the date she buys the car. A. How much can Sema afford to borrow? So you will hear car companies advertise 0 APR, meaning 0% interest. And just be aware that that means that the cost, the interest costs have been built into the price of the vehicle. So no one is going to loan you money for free. There's the incentive to offer 0% interest is built into the price. They've added that to be able to offer simple financing. Now, how much can Sema afford to borrow? We're talking about the regular payment that she's making for her car. The interest rate is 6.9 per year compounded monthly, so take the annual percentage rate, APR divided by 12. And here's our factor for calculating interest. And then the number of periods. If it's compounded monthly for 3 years, this is the number of times per year multiplied by the number of years. That's 36 different payments. So what is the present value now equivalent to making these regular payments? Substituting in our given variables, we get $9,730.34. So if she can afford to make these regular payments for this time, she can afford a car that costs this much. Now, how much interest will Sema pay on the loan? Using our formula, 300 times 36 is equal to $10,800. So really, this is how much she will be paying overall to be able to afford something that today costs this much. The difference between that is $1,069.66. So if it is urgent that you get this car, paying an additional $1,000 over 3 years might be an advantage for someone who is purchasing this vehicle.